have certain properties that seem obvious. I think the most obvious is that an object that's rolling has two distinct things that characterize it as an object that rolls. And the first is that there's this point on the ground that doesn't move with respect to the object, meaning that point and the ground are in contact and they are not moving with respect to each other. I mean, there's no sliding there. I know it seems like such a obvious thing, but it's far less than you might think. The fact that that point's in contact and there's no motion with respect to that part of the surface means that there can only be one kind of lateral force there, if at all. And that might be static friction. Might not be. That force doesn't have to exist at that point on the surface. A lot of people think friction has to be there, but not really. To be rolling, that point has to stay in contact with the surface and can't move with respect to the surface. That is the only condition that really has to be met to say that something is rolling. But that condition also brings with it a consequence. And the first consequence is that there must be synchronization between the angular variables and the linear variables due to the fact that that point is in contact. Now, you can have this synchronization and not be rolling. Like you can have something that's spinning at the same rate that it happens to be moving. That doesn't mean that it's rolling. The fact that there is this point in contact and the fact that we have this synchronization are the conditions for rolling. Now, I'm saying this very clearly because you're going to be asked to test whether an object meets the conditions for rolling. You see, an object can transition between rolling and sliding. And you have enough physics background at this point to be able to determine when those conditions are met and when those conditions are broken. So how much acceleration can a car actually apply to the wheels in order for it not to break friction and begin to leave a skid mark? How quickly can you apply the brakes and not have the wheels go from rolling to sliding? You have enough information now where you can determine these things. And these things actually require careful consideration. How many of you have ever been bowling before? Now, if you've ever been bowling, you watch a little kid throw the ball. They almost always roll the ball. Now, if you watch somebody who's more advanced, the ball tends to slide. But there's transition that occurs too. There are some people who throw the ball in such a way that between when it leaves their hand and before it meets the pins, it will transition between rolling while slipping to rolling without slipping. This description here is rolling without slipping, in contrast to rolling with slipping. When something is rolling with slipping, these conditions aren't met, even though there's a point of contact between the ball and the ground. Rolling without slipping, both conditions are met, which is why there's transition. So one of the FRQs from years ago had just a simple ring that was on a slick surface that hit a rough surface. And you had to figure out what the final velocity of the ring was going to be after it got slowed down by the friction, but began to spin up due to the friction. And knowing what the conditions for rolling are is a seminal part of that. Now, understanding rolling ultimately comes down to a couple of little features that we've already talked about. We're going to try and put them all together today. And to do so, I'm going to use just any object that rolls. Really I don't care what the shape is for the time being. I'm going to say that it has a moment of inertia I about its center of mass. And it has a radius, capital R. A mass M. and the surface has some coefficient of static friction. Now, to appreciate where we're going to go with this, I want to make sure that you bring to bear something I think that sounds so terribly obvious, but often gets overlooked, maybe because it's so obvious. An object's motion can't change unless there's an unbalanced force or an unbalanced torque. An object's motion can't change unless there's an unbalanced force or an unbalanced torque. Now, this part's important. That means friction is not required for an object to continue to roll. Friction is only required if you wish to change the rate at which something rolls. It's a misconception, and it's a big one. Friction isn't required for rolling. You can have an object with a point in contact and have all of these conditions met, yet it be on a slick surface. But that surface is unlikely to be able to stop the object's rolling. That surface is going to be unlikely to change the rate at which it rolls. So we tend to focus on situations where an object's rotational and translational motion are changing because they're more interesting. Some significant difference in an object sliding down a ramp. We've talked about objects sliding down a ramp before, and no matter what the shape of the object, if you have an object that's going to slide down a ramp, maybe not that shape, maybe this shape. This object's motion down the ramp is highly dependent on the angle of the ramp, the coefficient of friction, kinetic or static, not so much on its mass. We've done these problems enough to know that if there's no friction, the acceleration is just g sine theta. Hopefully you've done these enough to realize that even if there is friction, they're not particularly complicated. And if you don't remember these, you should be able to prove them on your own anyways. But that if the object's going to slide, it's going to be governed by those kinds of rules. And this is because we have our interplay of three forces. And we note that there's a definite connection between the friction and a normal force, and the normal force is angle dependent. This is all old school. Those forces are no different in a system that's going to be rolling. In fact, no matter what the shape of your object is, it's going to experience these same forces. So placing something that's round on the ramp doesn't change the fact that all of these forces are going to be the same. The problem is making the assumption that these forces will behave the same way. They don't necessarily. The first thing I want to remind you about before we ever get started here is that static friction is really what controls the situation of rolling, since this point in contact doesn't slide with respect to the surface. So for an object to be rolling, static friction has to take over. But static friction is governed by an inequality. And because it's governed by an inequality, we don't actually know how much friction is actually acting on the object. It's something less than or equal to this value. So the second misconception students make is that they assume that we're at the max. But I want to be very, very clear. You are seldom ever going to be at the max when it comes to static friction for an object that's rolling. It takes very little friction for an object to roll. Because of that, it's never ever close to the equal sign here, which means you are seldom able to use this in any calculation involving rolling. That's the first thing I want you to understand. That's your last resort in any rolling problem. Now, there is nothing different about an object that rolls when it comes to the net forces acting on it. The only difference is that those forces act at places that have the potential to cause torque. The normal force acts at the point of contact. It must be perpendicular to the surface. Therefore, the normal force is along a diagonal on our rolling object. The weight acts at the center of mass, straight downwards. And it might not be obvious, but the angle of the ramp would also be this angle here between weight and normal. And lastly, friction is going to act. It's going to try and oppose the one surface from sliding past the other. So I think assume pretty reasonably that frictional force will be up the ramp. Now, nothing about the object's translational motion is different than we've already talked about before. It's still going to be mg sine theta down the ramp minus friction equals ma. And it's still going to be normal minus mg cosine theta equals 0. The shape of the object doesn't contribute to those forces, doesn't change those forces in any way. Except we really can't figure out what the frictional force is. We don't have any easy way of determining what the static friction is, so I can't tell you how the object accelerates down the ramp. Right now, there's just not enough information to do so. And this should be obvious. Something different is going to happen to this object. The object's going to roll. We know that forces are the way in which we change energy and the way in which objects interact. We know that the object rolling is going to have more than one kind of energy. Knowing all these things should suggest to you that we're going to have to analyze this in a different way. A way that allows us to understand the rolling nature of it, the spinning nature, as much as its translational motion. So I don't think it's a surprise that when we reach a point now, we're probably going to have to take a look at the torque on the system. But here's where I would encourage you not to just do this blindly. It's really easy to think of this object as pivoting about its center of mass. The problem is the object doesn't actually pivot about its center of mass. When something rolls, this point isn't staying still. We tend to think that it's being spun that way, but that's not actually what's happening. An object that rolls is pivoting about the point of contact. The problem can be done by thinking of the center of mass being the pivot point, but it's more correct to consider the pivot point to be at the point of contact because this point doesn't move. So technically, that has to be the pivot, and the whole object is spinning about that pivot. The problem is that the instant that it moves to a new pivot point because a new point is in contact with the ground. So it's constantly creating a new pivot point all the time. So that's why we like to think of it as pivoting about its center, but that's not what's happening. The object moves slightly, creates a new pivot point, and now pivots about that new position. So with every micro change of its orientation, a new pivot point is created. We are looking at an instantaneous moment. The moment where it's currently pivoting about that point of contact. However, the best part about doing that is it eliminates two unknown forces. We don't know necessarily the frictional force. And although we can probably get the normal force, the one we definitely know the most is the weight. So it makes the most sense anyways to have a pivot point that eliminates forces we don't know. So we're going to go about that pivot point. And if we do, there's only one torque that acts about that pivot point. That torque is provided by the weight. That's what's causing the system to accelerate. Look, if we had put the pivot at the center, we would have eliminated the one thing that's actually causing it to roll. That's why it's also better to put the pivot here. Now, this part's not particularly hard to do. We know that the radius serves as our torque arm length. The force that's causing that torque is the weight of the object. And the sine of the angle is the sine of the angle of the ramp. All things we have access to in most problems. So this will represent the torque on the system. Now, for the object to be rolling, there's a special condition placed on alpha. If we think the object's rolling, then the condition placed on alpha is that it must equal the linear acceleration divided by the radius of our object. Now, here's the tricky part. First, this I isn't the moment of inertia of the object about its center. This I has to be the moment of inertia about the pivot point, which for every rolling object will have the same form. It's going to be I, center of mass, plus m radius squared. It has to be. We're shifting the pivot point from the center of mass to the edge. And that's still got to be A times R. Now, it's hard for you guys to judge when I'm getting to a point that's important and when I'm not. But I'm getting to a point that's quite important for you. And I want to bring all of these things that we know together. I want to do this on a different page so I can kind of highlight some important features here. Back a step. The acceleration is dependent on the rolling of the object. The only way to find the static frictional force is by eliminating the acceleration between these two relationships. It is the only way. There are three problems I'm going to expect you to be able to do. First, I'm going to expect you to be able to find what the frictional force is. This way. You can't use mu times the normal force. You're going to have to eliminate acceleration and find it this way. Second, there are conditions that have to be met, or an object will break friction and slide. You will have to learn when to do that. Those are the kind of problems we're going to do over the next couple of days, starting with a laboratory tomorrow on rolling. So first, mg sine theta minus friction equals ma. Generally, the frictional force and the acceleration are unknowns. We don't know how much they are. But in what we just solved, we have r, oops, I don't want to do that. I'll leave that white. R mg sine theta equals I center of mass plus m r squared times a over r. Yes, one of these is unknown, the a. But generally, we tend to know all the other things. We tend to know the mass of the object. We tend to know g. We know the angle. These are things that tend to be given to us, which means we could actually solve this for an expression for the acceleration right now based on the physical properties of the system without having to look at the forces at all. In fact, if you solve this for A, you get kind of an interesting answer. And by interesting, I mean you should know this answer. Now, that doesn't look particularly interesting on its own. I've just done the math for you. But I'm going to regroup it a little bit. First, I'm going to divide the top and bottom by 1 over r squared. That's going to make the top mg sine theta, and the bottom will be I, center of mass, divided by r squared, plus m. Now I'm going to group it a little different. I'm going to pull away everything that deals with inertia. For objects that just slid down the ramp, this was their acceleration, g sine theta. Now, objects that experience friction and slide are less than that. Objects that roll are also less than that. If we look in the denominator here is bigger than the numerator. This fraction is always going to be less than 1 for every object that rolls. So rolling objects roll down ramps slower than objects that slide without friction. But generally, they roll down ramps faster than objects that slide with friction. And we have a direct comparison. This is the acceleration for an object that rolls. That same object experiencing friction is going to have something directly subtracted from its acceleration. The next thing is everything about the object's rolling is completely about its inertia. Everything in the parentheses there is about the inertia of the system. And this is one of those features that goes without noticing. The whole first semester, we assumed that our objects had no rotational inertia, which made this 0. Please notice when it is 0, you just get g sine theta again. So rolling just adds a complication. It adds something to the inertia of the system. And this is the I center of mass. Remember, every single object that rolls is some fraction of mr squared. A hoop is mr squared. A ring is a hoop. A disc is 1/2 mr squared. A hollow ball is 2/3 mr squared. A solid ball is 2/5 mr squared. Are you kind of getting the point in here that the radius won't even matter when we have the object? That the radius is always going to cancel in some way, shape, or fashion. That these shapes boil down to the coefficients that are out front in what they add to the inertia of the system. Objects that are difficult to turn have a larger denominator than objects that are easier to turn. And it all affects the acceleration of the system. Now, just going in the overview here, but I would make this a big point of your notes. Now,